Good afternoon, everybody. Thank you for joining us this afternoon on our webinar with Apposite Technologies around their WAN emulation platform. My name is Craig Charles. I'm the Sales Manager at Open Reality. I'm going to just do a few sort of positioning slides on Open Reality and Apposite, and then we're going to pass over to Cade, who's one of the systems engineers at Apposite, who's going to do a live product demo. And then we're going to do questions and answers at the end. If you do have any questions, please use the chat box, and we'll open the lines up at the end of the session to answer any questions. Cool. So for those of you who are not familiar with Open Reality, so we've got a few strands to our business, but the kind of division, if you like, that's most relevant for this morning is our performance management portfolio. So we do a few different kind of areas in the kind of network performance space. Obviously, today we're going to be focusing around application and network testing, but we also have different technologies in place for monitoring the performance of applications, as well as various different acceleration and optimization techniques. Been around about 20 years, and Apposite is a product that we've been working with for yeah, kind of around about 10 years now, I suppose. So probably similar to the time I've been here. So yeah, we've seen the sort of product grow from a kind of more niche or use case, and I think we've seen the kind of the custom portfolio grow over time. And yeah, it's definitely a very useful product to have. So yeah, so Apposite has been around about 15 years. Like I said, we've been working with them for about 10 years. Certainly kind of now one of the sort of market leaders around, you know, kind of application and network performance testing. Yeah, particularly sort of their kind of use case, I suppose, is being able to predict the performance of applications before you roll them out under different WAN parameters. So as you can see, the customer base has been growing quite well, and yeah, we've worked quite well with them over the last 10 years or so. In terms of the customer profile, I mean, the use case is quite broad. I mean, there isn't one particular vertical market that would benefit from Apposite. Here's some, kind of examples of customers across, kind of telecom spaces and government enterprise. I mean, I suppose application developers would benefit from that, but really it's any customer that is rolling out a new application, upgrading an application, moving a data center, anybody that's really looking to do to test the performance over effectively different WAN parameters before the rolling out is suitable for an Apposite solution. So yeah, this kind of talks a little bit about kind of really the reason for using Apposite. I mean, I suppose ultimately it is about the user experience. I think applications, a lot of organizations will look at bandwidth as a good example, and if we go from a 10 meg to 100 meg to a gig, and certainly the kind of globally bandwidth is becoming more cheaper and readily available, but it's only really one piece of the puzzle, and whilst WAN congestion is sort of less of a problem in the current market, certainly there are lots of different network conditions that can impact the performance of an application from the user perspective, and obviously the common ones we see is around latency and jitter, and these can really impact the user experience. So a lot of businesses are now looking at it going, well, my network utilization is really low, but yeah, I'm still getting application performance issues. So that's where Apposite is really useful, so that you could predict and test these issues in advance before you roll them out and the users start to see a poor experience. It kind of talks about some of the sort of kind of projects that and initiatives that a lot of businesses are undertaking at the moment, which would benefit from network emulation. So I think that satellite applications are obviously very common for that. You've got very high latency sibling and satellite combinations. Kind of SD-WAN being quite a project in Internet of Things, but so the big one we're seeing at the moment is certainly cloud migrations. There's a lot of companies that are moving applications from users accessing on the LAN to the WAN for whether that be SaaS applications or infrastructure as a service, and certainly people are kind of maybe underestimating the impact to user experience for applications that are deployed over the WAN, particularly some of the legacy applications potentially that don't respond too well across the high latency or links with other parameters. I mean, in terms of what network emulation is, essentially, what Apposite would do in a lab environment will sit in between, effectively a client and an application server, and it allows you to dial in various different parameters, whether that be different bandwidth link speeds, mentioned around latency, packet loss, errors, just generally other impairments that allow you to kind of predict in a lab environment what experience would be affected by those different parameters. There are also different features which Kay will show you around recording live network conditions. So if you don't know of what the conditions are and you want to load them into Simulator, there are some recording software which we can do, which can build into the product. So we've got some actual real-world kind of use cases and deployments that Apposite have done. So I'm going to pass over to Kate, who's going to cover some of those, cover some of the actual physical models that are available in the range, and then take you through the interface and a live demo. I'm just going to put Kate as the presenter now. So Kate, you should have the should be the presenter now if you want to take over.
Let me know if you can see me.
Yep.
All right, great. So I'm going to whip through a few different use cases. As you see here, we have Lockheed Martin and the anti-ballistic missile defense system. This is a system that uses satellites to control the missiles. Obviously, anytime dealing with satellite connections, you're going to be dealing with a lot of latency, a lot of loss, and a very unstable network. So using our Network 10 gig emulator, they're able to create that kind of network to test their missile systems. Obviously, very important to be accurate and check to make sure that your missiles land where they're supposed to land. Our next use case is the aircraft control system. Again, this uses a lot of satellite links, from your control towers to the application servers and the clients. They all tie together to create a kind of central system. So you have many different types of connections coming in, some reports coming from satellite readings, other from LAN and WAN readings. So they actually use us to create several different types of networks, not only satellite, but WAN controllers, WAN conditions as well that are not terrestrial, we'll say. And they use us to create several different types of networks, what we call paths, which I'll jump into later. And this is General Dynamics uses this. Our next one is a mobile app testing using a company called Mobile Labs. This is a really interesting company. They've created a actual physical rack of up to 64 different types of mobile devices, whether they're iPhones, Droid, tablets, anything that can get on Wi-Fi or jump on networks using 3G, 4G, 5G, anything like that. We create different types of network conditions that they can test their mobile apps over. And what Mobile Labs does is actually creates an enclosure with 64 different devices that are controlled via USB. And this mobile device controller that sits in that rack actually can send commands as though someone is swiping or touching the touch screen. And so if you develop an app and you want to test it in a 3G environment, a 4G environment, a 5G environment, different types of Wi-Fi environments, and then run your tests as though someone is actually using that phone in those environments, we're able to give them all those different types of scenarios right there in their rack. And that's it. So here's our different NetHP models. You'll see that some of them have multiple ports. These are called different engines. For example, the N61 is a 1U server that has one engine, which means it has 2 data ports. And N91 has up to 8 data ports, which means that you have 4 emulators in one chassis. So for every 2 ports, every 2 paired ports, there's one emulator. So you can kind of think of port 1 as an ingress and port 2 as an egress, or vice versa. So each paired port represents one engine. So when we say engine, that means a emulator inside a chassis. So this N91, since it has 8 ports, has 4 emulators in one chassis. And this again is a 1U chassis. We have our 10G1, which is another single engine unit, a 10G2, which is a 2 engine unit, and 10G4, which is 4 engines or 4 emulators that run 10 gigabits. And then we have a 40G, and then we have our 100G product. So one thing I want to touch on right now is we're seeing a trend where our customers are buying 100G units, but only using them at 25 or 40 or 50G speeds, and they buy the 100G chassis so that they can upgrade later. So it would just be a small upgrade to increase your speeds in the future. We have our Linktree models. Again, it's a similar system. You have a single, in the Linktree model, we call, instead of calling them engines, we call them links. So this one has a single link, and the Linktree 8510 has 4 links. So again, that means there's 4 emulators running on one chassis. And of course, you have your management and console ports for controlling the Linktree and the NetHPs. Now we have our mini models. These are our kind of low cost, very simple, limited Linktree models. The Mini 2 goes up to 100 megabits, and then the Mini G goes up to 1 gigabit speeds. All the Linktree models, with the exception of the Mini, are 1 gigabit speeds. To go higher than 1 gigabit, to go up to 10 gigabit or 25 or 50 or 100, you would need a NetHP model. All right, so let me jump into a demo. I think you guys can still see my screen, right?
Yep, we can.
Great. So what I have in front of me is an N61 running our newest 4.0 code, which is actually going to be released in the next couple weeks. So you're getting a sneak peek. This is a single engine model, meaning you have only 2 data ports. It's important to know that the NetHP and the Linktree products all are what we call layer 2 bridge. So that means you put us in line. And if you were to do, so if I had a computer plugged into port 1 and a computer plugged into port 2, and I were to ping from port 1, I would to ping from one computer to another, or do an ARP or a trace route, you would not see us. You wouldn't even show, we wouldn't even show up as a MAC address. We're completely transparent, and we just inject our impairments in line. We can go into other non-layer 2 modes, but the majority of our customer, I would say 90 to 95% of our customers use us as a layer 2 bridge. Okay, over here we have our emulation toggle to turn it on and off. We have a detailed statistics screen. And then we have our paths and our endpoints. So that's kind of the important stuff. So I'm going to go ahead and create a path. I will use a actual real use case. We have a cruise line who uses us to provide not only internet access on their cruise ships, but also all their point of sales runs over the satellite connection, and so that way they can do credit card transactions, and they even do some video streaming of security cameras and stuff like that. So I will call this cruise line satellite communication. And I could come in here and create all my different bandwidths and delay. But for now, I'm just going to use one of our templates here. We have satellite templates. As you see, we have satellite good, satellite bad, low Earth orbit, mid Earth orbit, and geosynchronous Earth orbit. I'm actually going to use satellite bad, and let's see what it sets up. So it sets up 3 megabits down. So I have a download speed of 3 megabits. I'm sorry, that's wrong. That's a 3 megabits upload speed and a 5 megabits download speed. And in one direction, we're doing 450 milliseconds of delay to 1 second of delay. And we're dropping about 2.5 packets out of every 1,000. And then on the return trip, we have the similar settings as well. So if we were to do a ping time and do a round trip, it would be between 900 seconds and 2 seconds with packet reordering and dropping, about 50 packets out of 1,000. So I'm going to go ahead and create this path. And you see here it creates a visual rendering on our topology view of this cruise line SATCOM. So now I need to do some tests over this line. I happen to have 2 Linux servers on each side. I have a Linux server plugged in onto port 1 and a Linux server plugged into port 2. So I'm going to configure those as though they were my cruise ship and my cruise ship data center over here. So I'm going to do what we call creating an endpoint. So I'm going to create this endpoint, and maybe I'll call this cruise ship 1. And it is plugged into port 1 on the cruise line SATCOM path. And I need an IP address. So actually I'm going to log in and verify I have my right IP addresses. So let's go Linux 1. I'm just going to get the IP address of this Linux server. So it's 20.0.0.112. I'm going to put that IP address in here. Or I can do an entire network. I could do something like this. But for now, I'm just going to leave it a single IP. So I'm going to create this endpoint. Let me go back here. Let's do my ping. Now it looks like I have some traffic running on there. There we go. Okay, sorry, I was doing a test earlier. So now I'm going to create the data center that would be on the other side of this cruise line, that the cruise ship would be actually connecting to this data center to do their point of sales or allow internet access, or they were maybe their CCTVs on the cruise ship are broadcasting into the data center. So what I'll do is call this one data center, and that's plugged into port 2, and his IP address is 20.0.0.111. I'm going to create this endpoint, and now we have a one-to-one connection. So anyone with the IP address of 20.0.0.112 is now assigned to the cruise line SATCOM network, and anyone with the IP address of 20.0.0.111 is also assigned to the same network. But right now, you can see I'm pinging from 20.0.0.112, and I'm not seeing any latency. That's because by default, all my traffic is running over bypass and my emulation is turned off. So if I did everything correctly, if I turn on emulation, we should now see really ugly ping times, which we do. And we are now taking on those characteristics of the SATCOM cruise line network. So we can do many-to-one. So maybe you have more than one cruise ship out there. So maybe we have a cruise ship 2, and his IP address is 20.0.0.222. And now we see we have 2 cruise ships connected to the data center running over the cruise line network. And maybe you have a backup data center. And maybe he's 20.0.0.3. Great. So now we have a many-to-many example. So this is an actual customer setup. This is something that I helped them do their tests on, and they wanted to emulate a situation where the cruise ship was going into a snowstorm in Alaska, and they wanted to make sure that all their credit card sales. So the situation was actually rather interesting. They came to me and they said, would you be able to emulate a cruise ship going into a snowstorm? And what they found is if the weather outside was bad, everyone would come inside and either start gambling or spending money, and they were having problems getting their credit cards transactions to go through when they were in these snowstorms. So we were able to emulate that environment, and then they did their tweaking to their credit card authorization applications, and now using us, they can actually still make money while they're cruising through a snowstorm. So let's kind of jump in and do another quick scenario. We have a company that creates, that has a doorbell that when someone rings it, it calls your cell phone and you can talk to them. And so they may want to do some testing over a 3G or a 4G line or a 4G LTE. So I'll call this 4G LTE, and I'll choose my 4G LTE connection, and let's take a look at some of the settings. So we have 15 megabits download, 12.5 megabits upload, 50 millisecond round trip with packet reordering. And I'm going to create that. And now I'll create some endpoints for that. So maybe we have an iPhone here. Actually, and he's on port 1 of the 4G. And we'll just give him the IG address 192.168.2.22. Great. And maybe they have a droid. Right? And then on the other side, maybe they have their IoT device so they would set up something like this. Now this doorbell can run through the 4G LTE type connection in their lab and connect to iPhones and Droids and stuff like that. So I'm going to kind of go through some of our impairments to give you an idea of all the different types of things we can do. So if you look at this top row here, you kind of want to think of that as your egress or ingress, and then the bottom row is the return trip, or vice versa. So let's pretend the source of our data is over on port 1. It would run through and hit all these different impairments, hit the destination, and then return and hit all these lower impairments back to the source. So as you can see, we can set our bandwidth. We can set it in K, megabytes, or gigabits. Megabits or gigabits. We have something called background utilization. So I'll just give you an example of what this is. I have a customer who has a corporate network in all of North America and into the UK. So they have branch offices in London, New York, Chicago, Toronto, Seattle, and every day at 4 o'clock Pacific Standard Time, they have a job that runs, that backs up every workstation, every server, and every laptop on that network. It backs up all the data to a local storage. I believe it's in Chicago. And what they found is 80% of their bandwidth is used up by this application, these backup applications. So what we can do is we can emulate that situation where you have background traffic on the network. We don't actually send this out to your real network, but we can contain this traffic within our device. And if this is valid traffic that is contained within our devices and can interfere or chew up a lot of bandwidth while your other mission critical applications are running through it. So what they had is they had 2 or 3 other applications that needed to run while this backup job ran. So using us, they were able to recreate that situation and then tighten up not only their backup jobs, but these other mission critical applications. Okay, so queue limit, queue strategy, and framing overhead, these are all layer 2 kind of Ethernet impairments. These are just different settings that you can set. On the Ethernet side of things, I won't jump too far into that unless someone wants me to. Most of our customers don't touch this unless they are switching and routing companies. So we can support or act like we don't support jumbo framing. So a lot of times customers out there will have a product that requires jumbo frames, and then maybe it hits an old switch or an old router that can't handle jumbo frames and starts to fragment them. We can emulate that type of scenario, or we can just completely deny the jumbo frames. So the kind of secret sauce is in this middle column here, our WAN emulation. This is where you can set your different types of delays. So a lot of times people will jump in and say, okay, give me 50 millisecond delay in one direction and then give me 50 millisecond delay in the opposite direction. So this would give me 100 milliseconds round trip. So my ping would start at my source over here on port 1, run this way, hit 50 milliseconds and hit the destination, and then the return trip would get 50 milliseconds back. So you would see 100 milliseconds round trip. We have a few different delay models. So there's the constant, then there's uniform. This is how you create different types of jitter. So I can say anywhere between 20 and 120 milliseconds with packet reordering. This means if I were doing a ping, every second, it would be random delay. So this would be anywhere between 20 and 120 milliseconds of delay. So that's what most people call jitter. And there's different jitter types. We have exponential. This is where you can set your minimum, and maybe I'll say 20, and then the mean could be, we'll say 15. So that means that would be anywhere between 20 and 35 milliseconds of jitter. Then we can do normal. So this is the scientific meaning of normal. So here's our mean. This would be my average would be, we'll say 30 milliseconds with a standard deviation of 10. So this means I would be anywhere between 20 and 40 milliseconds of latency, but it would average out around 30 milliseconds. And then we have an accumulative burst. So this is when you can have bursts of delay for a certain amount of packets, and then it then would go back down to reasonable amounts. This is very popular with our SATCOM customers. So go ahead and turn that constant. So we also have different loss models. So we have a random loss. So if I were to do 1% loss, this means I would drop 1 out of 100 packets. If I were to do 0.1, that'd be dropping 1 out of 1,000 packets. If I were to do 0.01, 1 out of 10,000, 1 out of 100,000, 1 out of 1,000,000. So we can drop, we can get very granular when configuring your loss model. We can have bursts of loss. So a lot of times when we see loss, it could be a switch or a router on your network who's having problems, and maybe it's getting buffer overrun. And if your switch or router starts getting buffer overrun, the way it recovers is it just drops its entire buffer. So we can have a probability and then have a minimum amount of packets. So maybe we'll say we'll burst anywhere from 5 to 25 packets of drop packets, and we'll give a 1% likeliness of that happening. So that's our burst. We have a periodic, which is, every 100 packets drop 1, or you can say every 10,000 packets drop 1 packet, or drop 5 packets, something like that. Gilbert-Elliott. This used to be really hard for me to explain to people. There's actually a wiki page on the Gilbert-Elliott test model. But the easiest way for me to describe to you what a Gilbert-Elliott loss is partly cloudy in a satellite environment. So you have your good states where there's no clouds blocking your satellite, and then you have your bad state when you do have clouds in your way, and these are kind of chosen at random. So if you ever want a fun read, you can read up on the Gilbert-Elliott good state, bad state testing model. And then we have a bit error rate, which is just a mathematical formula for your losses. It's a great read in our manual as well. Okay, so we have a network outage. So I could say, okay, every 10 minutes, which is 600 seconds, give me a 5-second outage. Or if you're in the satellite world, you can say, okay, every 1 to 8 seconds, give me a 0.001 outage. So give me a 100 microsecond outage every 1 to 8 seconds, and choose that at random. This is called flapping in the satellite community, and yes, we can support that. Okay, so now we have bit error rate corruption. The easiest way for me to explain this is for those of you who are familiar with, HP, Cisco, Juniper switches. If you do a show interface and you start seeing what we call CRC errors or collision errors, we are able to duplicate those. And then we can do different types of packet reordering. So a lot of you might know that TCP and UDP, a lot of times there's multiple paths to the same destination, and maybe path 100 arrives before packet 75 does. Some applications can recover from that, some can't, and this is a way we can duplicate that environment. And then we have packet duplication. So I normally use UDP as an example, whereas UDP just kind of fire and forgets, and you get a lot of duplicate packets out there. And some applications don't know what to do when it starts seeing duplicates of the same packets. It tries to incorporate them, and it can mess things up, especially with video streaming. And of course, everything I just showed you can be done on the return path as well. So we're very granular. We can create environments where your downloads have a different network than your upload does. So very helpful when testing SD-WAN or other WAN environments as well. So that's a quick tour. I also have the API to show you. So everything I've done here, I can also do using API scripting. It uses RESTful API and JSON formats. Before I jump into that, does anyone have any questions? No?
No questions at this point, Kate.
Great, thanks. All right, so now I'm going to jump into something that's a little more advanced. This is for the people who are really good with automating and creating scripts to automate your tests and creating different environments. So we do have a fully integrated RESTful API. I'm going to do some quick examples. I've written some of my own scripts to quickly do tests. So the first thing I'm going to do, I'm going to create a login. I'm just going to log in and authenticate. So I've logged in as the user admin, and now I'm just going to clean up my environment. So what I'm going to do is I'm going to hit enter here, and as we watch here, we'll start to see everything disappear. I've deleted all my endpoints, and now I've deleted my paths. And great. So we actually have another product called the Traffic Jam products, which is a traffic generating tool. So what I'm going to do is I'm going to start my traffic generation, and I will see that traffic is going through the Network here. We see it's getting 1 gig speeds, and it's going through the bypass, and my emulation is turned on here. So what I'm going to do now is I'm going to quickly create an environment for my traffic jam traffic to run through using my script called build traffic jam. So I'm going to fire that off, and we should see it build the environment for traffic jam. So 500 megabit, 100 milliseconds latency. So if I come and look at my traffic jam, I can see as soon as I built my environment and turned on emulation, I took a performance hit. And I can also see this data running on this path here. There we go. And we see it's getting 400 megabits, roughly around 400 megabit throughput. I can also come in here to my detailed statistics and choose my traffic jam path and see my data running through there as well. So you'll see here in one direction I'm sending around 400 megabits, And on the other side, even though this orange line is up higher, if you look over here, it's only 3.8 megabits. So the blue is on this side, which is 400 megabits, and the orange on this side is 3.8 megabits. So we're only sending traffic in one direction. So what's kind of fun to do is we can actually watch our performance take hits when we start messing with different impairments. So maybe let's add a little bit of loss and see what happens. I'm going to add 1% loss on this traffic generation. So I'll apply that. Let's go look and see what happened. Oh wow, huge loss. So just dropping one packet out of 100 pretty much destroyed my transfer. So let's take a look at that. So yeah, oops, let's go here. So here we can see where I put that 1% loss. We went all the way down to around a megabit throughput. That's just loss. So that just gives you an idea how loss can affect things. Let's take out that loss. Oh, actually, let's have some fun. Let's take out. So now we go back up to 1 gigabit because I destroyed the environment. So just to give you an idea of what a typical API command looks like. Actually, let's rebuild. So here's another network that I'm going to quickly build. This is the 2 Linux boxes that I was doing before. Okay, and so I'm just going to do a quick query of the endpoints. So first I'm going to authenticate. And now let's do a query of what the different endpoints look like. Our path, we'll do this path right here. So this is what the automation looks like. If you're familiar with RESTful API, it will make sense, but it gives you all your information in JSON format. So here we see we have a path called 100 megabit line 70 milliseconds. It's 100 megabits in one direction, 100 megabits in the opposite direction, and we have latency as constant at 35 milliseconds in one direction, 35 milliseconds in the opposite direction. So if we look here, that's this exact path, 100 megabits, 100 megabits, 35, 35. So if I were to build my traffic jam lab again, and let's look at the paths. We'll now have 2 different paths. So now we see our traffic jam path as well as our 100 megabit line. So maybe I would like to see what's going on with my endpoints. I can just change this to endpoint. It should give me all 4 of my endpoints. Linux 1, Linux 2, traffic jam port 1, traffic jam port 2. So Linux 1 with this IP address, Linux 2 with this IP address, traffic jam port 1 with this IP address, and port 2. So that's how you can automate things. You can also download all of your statistics in a CSV format. And then we have some other pretty cool features where you can save all your engine configurations and restore them. We have something called the Netropy recorder. I think I got one here. Let's see. Oh, I don't have it installed. So I'll explain what the Netropy recorder is. It's a free application that can run on a Droid, Linux, or Windows box. And what it does is if you have a client out there, I'll actually give you an example. We have a customer who has a set-top box that connects to your television and you stream video to it. And sometimes the customer will have problems, say, hey, I can't watch this video. It works a little bit and then it buffers out and then it freezes and then it stops and it gives me an error and it's not working. And if this company believes this could be a network issue, they've actually installed the Netropy recorder inside of their set-top box. We gave them the source code and they just log into that set-top box and they hit record and they say, okay, sir or madam, please try watching that video again. That user will then go and try and watch that video and it'll eventually fail. They then hit stop on that Netropy recorder and they can download what's called the recorder file, and then they can load that inside the Netropy. And what that does is it gives the exact network conditions that that user was seeing. It doesn't replay the traffic, but it gives them the bandwidth, the latency, the loss, the duplicate packets, and the corrupt packets, and it replays that within the Netropy. So you can get a real-world environment in your lab to try and duplicate the issue in the lab. Hopefully that makes sense. So that's kind of a mid to deep dive into the Netropy. I think I'm done. Does anyone have any other questions?
Okay, there was a question about whether there's a virtual edition of this.
Yes, we have a virtual edition as well as a cloud edition, so we can run in VMware or KVM in Linux models, and then we're also in Amazon Cloud right now, and we're going to be pushing out to Azure and Google as well.
Perfect, thanks, Cade. Don't think we've got any further questions at this point. So just have one more question through saying, what's the licensing model for Netropy?
So Norm, well, actually, I'm not the sales guy. So Richard might be the better one to answer that question than me.
I can cover that, Cade, if you want. It's great.
Yes.
So essentially, there's two kind of, depending on the variant. So obviously, if it's a 1 gig model, pretty much comes with a 1 gig license. If you're going for a 10 gig or a 40 gig model, you can license each appliance to a lower bandwidth amount. So on a 10 gig box, for example, you could go with a 1 gig license initially and then upgrade it to 10 gig. Essentially, there's different hardware appliances, which Cade covered at the beginning, which have sort of different price points depending on whether it's a Linktree or a Netropy, or if it has multiple WAN links. But we've got brochures, so we can send brochures out which have pricing on them with all the licensing cost, etc. There is a, as well as the hardware purchase, there is a 1 or a 3 year right to use license, which basically includes your product updates, your maintenance, sort of hardware warranty, technical support, and just the license to use the product. So yeah, that's all on the brochure, so we can share that with the people on the session.
Thanks, Craig. Okay.
Awesome. I had one more thing to add. We're currently looking at an N61 model, but no matter what model of Netropy you log into, they're all going to look the same and behave the same way, just obviously different speeds. So once you learn one of our products, you're going to know how to use the rest of the products on the same line.
Okay. Cade, thank you very much for your time and the demonstration. If anybody would like to see the solution in a bit more detail and run it through sort of in a one-to-one discussion, then obviously please reach out to somebody at Open Reality and we'd be happy to arrange a further demonstration or provide you with some pricing. Thank you everyone for your time and we hope to see you soon. Thank you, Cade.
Thank you. Have a great day.
You too.